Good morning, everyone. Today, we are going to start a new module that is Z transforms, and it is applicable to only discrete time systems. So, let us discuss in detail about Z transforms in this video. We are going to cover the introduction aspects of Z transforms. Later on, we are going to cover some of the sequences that are being involved in Z transforms, and later on, we are going to see some properties that are associated with respect to the Z transforms again, and later we will conclude with some few problems. In this entire video lecture session, we are going to cover Z transforms, properties of it, and we are going to discuss few problems related to it and how the property is being applied to a Z transform. So without any further change, we are going to move with the Z transforms. I'll write here. So in module number 5, in module number 5, sorry, in module number 5, yes. So module number 5, we are going to deal with Z transforms. We are going to deal with Z transforms. Okay. So first we will discuss about some introduction about Z transforms, and in that introduction why we need Z transforms, the origin of it, and how it is related to a discrete time signal, and so on. We are going to see with it, and certain application level where we are going to use Z transforms, we are going to deal with it. So later we will define a Z transform. We will define a Z transform. We will define a Z transform. Mathematically, we are going to define the Z transform of a discrete time signal, and later we are going to deal with certain properties of Z transform, properties of Z transform. Okay, so later we will solve some numerical problems. So this entire video lecture session will be with respect to the Z transforms and certain concepts that we had written here. So that is the introduction, that is the definition of a Z transform, properties of Z transforms, and numerical problems of Z transforms. So we are going to cover all these things in this video lecture session, and it is entirely the video subject that is there for electrical engineering students of 5th semester under 18 scheme 18EE 54. We are going to deal with the subject called as signals and systems. Signals and systems. Okay, so this is the concept whatever that we are going to discuss. Now when I talk about the introduction as of any Z transform, so we have a discrete time signal, say x of n. I'll write it here as a discrete time signal, as a discrete time signal. So this discrete time signal, whatever that we are going to discuss, so it is being written in the form of a difference equation. So any discrete time signal, that is x of n, so having the delay and the advanced signal, delay signal, or the advanced signal that is there, delayed signal, or the advanced signal that is there. So any discrete time system is being modeled with the help of a difference equation, is being modeled in terms of the difference equation. So now this difference equation, so if I want to express it in Z domain, so as I already told you, you need to be clear with the aspect of engineering mathematics as a prerequisite. So this Z transform that is there, that we are going to discuss now. So the term Z refers to a complex number here. The term Z refers to a complex number. So this complex number, if I want to represent it, I can represent it with the exponential form as r into e power j omega, that is there. So that is r cos omega plus j sine omega. I can write it like this in terms of the a plus jb form. So where r is the radius vector that is there, we can have the z plane, which I can represent it as the real part of the complex number as the x-axis or the horizontal axis, and the imaginary part of it associated with j imaginary part of z. that is there, that can be represented for the y-axis, and this radius vector that is there, that is the radius of the circle, and omega is the angle that is associated with it. So now when I talk about this difference equation, I can write any difference equation in a simple manner, and I can write this difference equation which is to be solved. So this difference equation modeled from a discrete time system can be linked to a Z transform there. So how it has been linked? So any Z transform that you need to get, it plays a major role in transforming the linear difference equation into a algebraic equation. So how you can model it? So you can write the linear difference equation that is there, the linear difference equation. I need to model it in terms of the algebraic equation here. I need to model it in terms of the algebraic equation here. So this algebraic equation that is there, which is obtained from the linear difference equation, I need to have the Z transform, transforming from domain, that is the discrete time domain, in terms of the algebraic equation. I need to have the Z transform approach here, right? So now you can generally have any discrete time system being written in terms of the algebraic equation. To solve it easily, so we need to go for the Z transform approach. So now you have generally in the coming modules we will be discussing about DTFT, that is discrete time Fourier transform, and DTFS, that is the discrete time Fourier series. So discrete time Fourier transform, and certainly we'll be having the continuous time Fourier transform also, and continuous time Fourier series, continuous time Fourier transform, and discrete time Fourier transform. Okay, so what is the major difference that you come across in discrete time Fourier transform and continuous time Fourier transform is you are going to have the signal, whatever that is associated as continuously varying with respect to time in continuous time Fourier transform, and in discrete time Fourier transform you are going to have the discrete nature of it. So that is one aspect, one simple aspect that is covered, and later on we'll be having again the properties that are associated, and you have certain laws which you can include it, and you can transform it certainly depending on the signal that is there. So coming to the major aspect here, if I model it in terms of the algebraic equation in the Z domain especially, so this algebraic equation will be expressed in Z. So generally it is any discrete time signal. If I want to have the Z transform being applied, so it will be in terms of the algebraic equation, and this algebraic equation will be the Z domain itself. So it's the function of Z, like f of Z. If I want to express it, it will be in terms of 1 plus Z plus 2Z generally, or that would be 1 plus Z inverse plus 2 times Z inverse, or something like that. Okay, so it keeps on varying depending on the signal that you have been applied. Okay, so now if I want to analyze the system characteristics, any discrete time system will have certain system characteristics, right? So any discrete time system will have certain system characteristics. System characteristics. Okay, so this system characteristics that is there, either it might be linear in nature, whether you have to verify it is linear in nature, or it is stable, the very important aspect of any system or a discrete time system, or you will be having the causality nature of it, or memory aspect, memory or memoryless. Memory is one thing. So there are many such system properties or system characteristics which are there for a discrete time system or any system in general there. So now in order to have this discrete time system, which is the common way in which you can express it in terms of any computational structure or a computational way, like a computer, like any digital device which is to be connected. So the digital signal plays a major role here. So this system characteristics such as linear, stable, causality, and memory is entirely dependent on the equation that you are modeling there. So this equation, what you are going to have it. So in order to solve it quite easily, we are going for the transform approach, right? So the word transform itself, it needs to be transformed. Like for example, if I want to go from one domain to the other domain in to solve it quite easily, right? So and again, coming back to the normal approach, we can have the transform being done for a certain signal there. Either it might be a continuous time signal. In continuous time signal, we are going for the Laplacian approach, that is the Laplace transform approach. In the discrete time system, we are going to have the Z transform approach being present there, right? So that is one thing where you can find certain applications in terms of the discrete time system, right? So now we talked about the discrete time Fourier transform, right? So in discrete time Fourier transform, and when you compare with the Z transform, so you would have generally, once you deal with the discrete time Fourier transform, I'll tell you the reason now. So the Z transform is nothing but the extended version of the discrete time Fourier transform. The discrete time Fourier transform, it doesn't converge, and the Z transform generally converges. So I'll talk about the region of convergence also, which I term it as ROC. So region of convergence, right? So ROC, that is there, and you don't have the converging nature in terms of the discrete time Fourier transform, and in this Z transform, we are going to have the convergence nature of it. Okay, so how do you define Z transform is the major aspect here. Let us start analyzing it in a mathematical way. So Z transform, if I want to define it, so for any discrete signal, discrete time signal x of n, discrete time signal x of n. So the Z transform is defined as the Z transform is defined as x of z. So that is the Z transform of the given signal. How you can generally analyze it? Z transform of x of n. So that would be equal to x of z. So that would be equal to, I can write it here also, Z transform of the given discrete signal. I can represent it as x of z. It is represented in the summation 1, where the summation range will be from minus infinity to plus infinity, x of n, z power minus n. Okay, so this is how I can define the Z transform, that is x of z. That would be equal to sigma n equals minus infinity to plus infinity, x of n, z power minus n. So this is the Z transform expressed mathematically. X of z, that would be equal to sigma n equals minus infinity to plus infinity, x of n, z power minus n. So that's how I can write the Z transform of any discrete signal. So x of n, I can write it like this. That is symbolically, that I can write it in terms of the definition there. So x of n would be like related to x of z using the Z transform approach. So the range of integers, I just wanted to talk here. The range of integers will be from minus infinity to plus infinity. Okay, so minus infinity to plus infinity, any range of integers that is taken into consideration, I'll be having the Z transform defined over the summation of the ranges there, right? So any Z is nothing but a complex variable. So here, when I talk about the mathematical way of expressing it mathematically, okay, I just expressed the Z transform as x of z. That would be equal to summation n equals minus infinity to plus infinity, that is x of n, z power minus n, that is there, that is x of z. So this range, that is minus infinity to plus infinity, that would be the range of all integers, where the Z transform is applicable. So this is the discrete time signal, and Z power minus n is associated with it, right? So that is how you can define the Z transform, that is summation n will be from minus infinity to plus infinity x of n into Z power minus n. So I can call this type of transform node. You can just analyze it as I discuss later on with left-handed sequence, right-handed sequence, and this sequence especially is called as the sequence will be termed as a double-sided sequence. A double-sided sequence. So this is entirely with respect to the double-sided sequence or two-sided sequence, or the Z transform of it will be the double-sided Z transform. The double-sided Z transform. Okay, so that is how I can term it, or I can define it like that. Okay, so that is the double-sided Z transform there. Okay, so now most important aspect here when I talk about a region of convergence, which is directly related to the stability of any discrete time system, ROC. It is meant as the region of convergence. The region of convergence, ROC. So now how I define the region of convergence is the set of Z values, for which the summation converges. Is called as region of convergence. Region of convergence, ROC. Okay, so when I talk about the summation converges, I have the set of Z values. You certainly define it as the region of convergence. So let us analyze whatever that I have written here. So set of Z values, as I told you, it would be ranging from minus infinity to plus infinity. So these are the set of integers that are being present, and the set of Z values which are present of the algebraic equation, and you have a summation that is present there, right? So let me talk about summation like this. That would be from, say, minus 2 to plus 2. I have a signal that is x of n. That would be my Z, that is written in terms of the Z transform as sigma n is equal to minus 2 to plus 2 x of n Z power minus n. So if I want to expand this summation, you will get a value in terms of the x of Z. That is the algebraic expression. That is there. Okay, so that is entirely in terms of Z. So if I want to expand this summation and I get the algebraic expression that is there, x of Z would be equal to sigma that have a summation with x of n times Z power minus n there. So this summation, whatever that is expressed as an algebraic expression, once I take the summation of it, so you say it to be converging. So it has a finite value. What we can generally come across is it has a finite value there. So over which the set of Z values are ranging, and there you are going to have the summation which is being converging in nature. So such a region of convergence. So region where you'll be having certain region there that would be from minus 2 to plus 2 or something like that, minus 3 to plus 3 or something like that. So that entire region where you'll be calling or where you will be defining this Z transform is said to be converging in nature, right? So the entire sum, if you take the sum of that region, that whatever the Z values that are coming over there, you can call it to be the convergent nature of the summation that is there. So you call it to be the region of convergence. That is the region in which the values are said to be converging in nature. So that is how you can define the region of convergence there. Okay, so now if I have two regions, what I can express it, I can express it in Z plane here. So if I talk this as a Z plane, any plane represented in a 2D axis there, so I can call it to be the Z plane there, real part of the real part of the complex number as the horizontal axis, and the j times imaginary axis that is there. Okay, so now if I want to talk about this Z plane entirely, so I have this region of convergence, as I already told you. So you have the circle which is there, the radius vector will form the radius of the circle there, and you have certain angle that is present there. So either depending on the nature of the Z transform that you've been obtained, you can call the regions to be present there. Generally, it would be an annular region if you have more than one or two signals that are being present there. So this annular region that is present is called to be the region of convergence. Like I can just write it like this. Okay, I can just write it like this. It would be for a left-handed sequence what I'm writing now. So annular region of the Z transform of a signal, of a discrete signal, say let it be specific, of a discrete signal, is generally called as an ROC. So I have region 1 to be present there. Okay, next I have region 2. So this values of Z, what I can write here is generally the region of convergence. So this one R1 and this one is R2 there. So that is region of convergence 1. Region of convergence 1. So next R2 will be a region of convergence 2. Okay, this is mod Z. So when I say mod Z here, so either it might be the positive values and the negative values that is there. So Z, which I talk, it is entirely present for both positive values of Z and also the negative values of Z. If I want to take the modulo, that is nothing but the magnitude which is associated with it, right? So now if I want to talk only about one-sided sequence there, so only about one-sided sequence, it is generally called as causal sequence there, only like one-sided sequence that is present there. So if x of n is a causal signal or a causal sequence, okay, I can call this to be a causal signal or a causal signal, sequence that are being present. When I talk about sequence, you will be having it as the like any discrete nature which has been expressed. I can call it to be a causal sequence there. So now for n less than 0, x of n would be equal to 0, then its Z transform, is, say, x1 of Z, that would be equal to sigma n is equal to 0 to infinity x of n Z power minus n. So this type of representing the Z transform, that is x1 of Z, is said to be the unilateral Z transform. So this type of sequence where x of n is a causal signal. So for any values, as I already told you, n would be ranging from minus infinity to plus infinity. So let me cut down the summation where it would be from 0 to infinity, only one part of the sequence there. So how I can represent any signal like this, say x of n, so this is n, so this would be from 0 to the right side. Okay, so 0, 1, 2, 3, 4, something like that. It keeps on going, or depending on certain set of values, you can have the discrete signal as x of n, you can write that discrete signal as a unilateral Z transform, say that is x1 of Z. So this x1 of Z, which is defined as a unilateral transform, will have n equals 0 to infinity. Only these values, that is the positive integer values that are being present there, you can analyze such transforms to be unilateral transform or right-handed or one-sided sequence. Okay, right-handed sequence can also be written right-handed sequence, okay, or one-sided sequence, okay, one-sided sequence, or left-handed would be right. So one-sided generally refers to the right-handed itself. So if I have x of n to be a causal signal or a causal sequence, I can have the right-handed sequence to be written in Z transform as x1 of Z to be equal to sigma n is equal to 0 to infinity x of n into Z power minus n, and x1 of Z, whatever I have written here for the Z transform of the right-handed sequence, it is said to be the unilateral Z transform then. Okay, so now let me move on to the next one, that is the Z transforms. One important aspect I wanted to highlight is the Z transform. Here we are going to discuss again, that is the Z transform and region of convergence of finite duration sequences. Okay, so another topic, the Z transform and region of convergence of finite duration sequences. Okay, look the word that I have written there. So it is the finite duration here. So once when I talk about the infinite duration, you will be having it has been modeled like a power n, so where n would be like ranging from 0 to capital N minus 1 and so on. So when I talk about this finite duration sequence, I will be having x of n being defined like this. Okay, so let it be from 0, 1, 1, 2 or something like that. Okay, so as I already pointed out in linear time invariant system, I have the arrow mark here. So the arrow mark, if I want to represent it, this arrow mark will be like n is equal to 0, like n is equal to 0 here. Okay, so now at the same point you are going to have n is equal to 1 here. So from n is equal to 0, if I move towards the right, so if I move towards here, that would be the positive values of n. Okay, so let me write it here, x of n. If I write it, so if I want to express like this, okay, I would have written the x of n signal here. So this would be n is equal to 0, this is n is equal to 1, this is n is equal to 2, this is n is equal to 3. Now x of n, that is 1, 2, 4 minus 2. Okay, so if I want to have the arrow mark here, so the arrow mark, if you can write it from the down or from the upward direction, you are going to have it the point or the number whatever that has been pointed here. So that is 4, that is n is equal to 0, this is n is equal to minus 1, that is n is equal to minus 2, this one is n is equal to 1. So if I move towards the right, that would be n is equal to 1 here. So from the arrow mark, it is right, that is n is equal to 1, that is positive 1. And if I move it towards the left, that is n is equal to minus 1 and n is equal to minus 2. So this is how I can represent a discrete time signal there. Okay, so I can write it as x1 or x2 of n, whatever it is. So any discrete signal, any discrete signal, discrete time, finite duration sequence. Okay, finite duration sequence. When I talk about finite duration sequence here, so it would be from 0, 1, 2 and 3. So the total number of samples will be 4 there. So I have taken the total number of samples to be 4, 5 or whatever it is. I just wanted to convey that this arrow mark, if I want to represent, so if it is like pointing out towards one of the numbers here, so if I move towards the right like this, that would be from n is equal to 1, 2 and 3. That is the positive sequence. And n, if it is represented here, this is the second one, So where n is equal to -1 and -2 towards the left hand side. This one is the right handed and this one is the left handed, where the arrow mark points at the origin or at 0. Okay, keeping these fundamental aspects in mind, and I can move on to the first sequence, that is nothing but the right-handed sequence. Right-handed sequence. Okay, that is the right-handed sequence. A right-handed sequence can be defined as a right-handed sequence. A right-handed sequence can be defined as x of n will be equal to 0 for all n less than n naught, where n naught is positive or negative, okay, is positive or negative, but it is finite, okay. So if n naught greater than or equal to 0, the resulting sequence is said to be a causal sequence. Or positive time sequence, Okay, so for a causal finite sequence, for a causal finite sequence, the region of convergence is entire z plane, except at z equals 0, except at z equals 0. X of n will be, like, for example, if I want to write it, so it would be 1 2 2 1. I have taken it as a discrete time sequence as 1 2 2 1. So if I want to have the z transform of it as x of z, that is z transform of x of n, how do I write it? I can write this z transform to be, yes, so if I want to apply here, so yes, yeah. So how do I write this z transform? X of z, that would be from sigma n is equal to 0 to 3 x of n z power minus n. So that is x of 0 plus x of 1 z power minus 1 plus x of 2 z power minus 2 plus x of 3 z power minus 3. So what is x of 0? So look here carefully. I have not this. What it means? So this is at n is equal to 0. That is 1 plus, what is x of 1? This is 1. That is x of 1, and this is x of 2, and this is x of 3. Okay. So that is 2 times z power minus 1 plus 2 times z power minus 2 plus 1 into z power minus 3. Okay, 1 plus 2 divided by z plus 2 divided by z square plus 1 divided by z cube. Okay, I'll take the common factor, or you can just write it here itself, not a problem. So you can have the values of z. Okay, so where it converges. Okay, so I need to define the ROC now, right? So to define ROC, as I already told you in this definition of the right-handed side sequence, it is the entire z plane, entire z plane, entire z plane, except at z equals 0, except at z equals 0 there. So this is how I define it for the right-handed sequence. Right-handed sequence. This is how I can define it for the right-handed sequence. So this is the entire z plane is the region of convergence. That is the entire z plane except at z is equal to 0 would be the equation, or you will be having the summation where it converges to a finite value. So just give z is equal to 0 here. You will be having x of z to be equal to infinity there. So that's not like that's not a way in which you can write it, or where you can express it in terms of the algebraic equation. So at z is equal to 0, it will be having z is equal to 0, x of z will be equal to infinity at z is equal to 0. So any other values that you give, say z is equal to 1, z is equal to 1.5 or something like that. So there you will be having the finite value, or where you can have x of z to be converging to some finite value which is present there. Only the entire z plane, entire z values that you give, except at z is equal to 0, you are going to call this to be the region of convergence. So the region in which where you can see certain aspects, you will be having the finite sequence values, you will be calling that to be the entire z plane as the ROC, except at z is equal to 0 for a right-handed sequence there. So that's how we can define it for a right-handed sequence. Okay. So next, going on to the next one, you are going to have the left-handed sequence. We're going to call it for the left-handed sequence. The left-handed sequence. So if I want to talk about the left-handed sequence, so I can call a left-handed sequence to be x of n, any signal which is equal to 0 for all n greater than n naught, for n greater than n naught, where n naught is positive or negative, is positive or negative, is positive or negative, but finite. But finite. If n less than or equal to n naught, if n less than or equal to n naught, it results in an anti-causal nature of the sequence, anti-causal nature of the sequence x of n. Anti-causal nature of the sequence x of n. So x of n is said to be anti-causal in nature, so it is non-causal in nature there. So x of n will be equal for all n greater than n naught, where n naught is either positive or negative but finite. So if n less than or equal to n naught, it results in a non-causal sequence, that is x of n. So x of n is said to be non-causal in nature. So the region of convergence is the entire z plane. The region of convergence ROC is the entire z plane, except at z equals infinity. At z equals infinity. Observe carefully here. Let me write a sequence x of n to be some sequence like this. Okay, so where it is said to be a left-handed sequence. So once I talk about left-handed sequence, where is the arrow marking? At n is equal to 0, it is marking at 2 here, right? So now if I want to define x of z, so that would be the summation, which would be from -1 here, this is -1, -2, and this is -3. Okay, n equals -3 to 0, x of n, z power -n. So that is x of z. Okay, so if I want to write it like this, I'll be having z cube. Okay, so next plus 2z squared plus z plus 2. Okay, so this is how I can write the z transform. So x of z would be equal to z cube plus 2z squared plus z plus 2. So that is how x of z is written. So this is x of z, that is the z transform of the given signal there. Okay, so just hold for a while.